Thank you, everyone, for coming. This is the final round of the MIT 150 Exploration Competition. This competition was announced in January with the intent of getting students at MIT brainstorming about exploration ideas. And the most intriguing of these ideas are going to be presented here. The questions posed by the competition were as follows. In the next 50 to 100 years, where will we go? What will we do there? How will we get there? We have 5 teams competing in the final round, but to get this point, they had to survive 2 rounds of down selection, including a presentation in front of MIT faculty 4 weeks ago. At stake is $8,000 in cash prizes, including $4,000 for the top exploration idea, sponsored by XCOR Aerospace. Each team will have 5 to 7 minutes to pitch their idea for the future of exploration, and then they will spend a few minutes fielding questions from the judging panel. We have 4 judges over here. We have Andrew Nelson, the Chief Operating Officer for XCOR Aerospace, Mike Massimino, an MIT alumnus and astronaut who participated in a recent repair of the Hubble Space Telescope. James Bellingham is Chief Technologist for the Monterey Bay Aquarium Research Institute, and Professor John Hansman from Course 16, also Director of the International Center for Air Transportation. The judges hold most of the weight in determining the winners, but audience voting will also be a factor. After the last presentation, we will be putting up information on the screen for SMS text message voting, and we'll encourage you to have your mobile devices ready. Without further ado, we will introduce our first student team. Jennifer Booz is a recent graduate of MIT, class of 2010, and is completing a 5th-year master's degree in the Department of Earth, Atmospheric, and Planetary Sciences, where she studies paleomagnetism in lunar rock samples. Her presentation is called Satellite Play.
Hello. Satellite Play is a means for connecting players on Earth to robots on the moon via a massively distributed, mediated exploration experience. In 1969, families gathered in their living rooms to watch the first astronauts set foot on the moon. By 2069, we propose that families will gather in their living rooms to set foot on the moon themselves. Satellite Play updates exploration to the digital age by connecting users to uncharted territories for them to chart at will. A common digital terrain map model is generated by the players as they explore. Logging on to Satellite Play, either through game console or website, you will be able to select from 3 on-surface robots. You can pick from robots that are readily available for you to play immediately, or you can select to take part in a greater mission in the future. You can also look at trails which have already been blazed, or explore raw output from current active users. This is our first robot, a simple yet rugged hopper, the most accessible of our robots. We expect it to cost about $5 for half an hour of hopping on the moon. This raw feed would be displayed in your living room, and you also have the option to view data that you are collecting as you're hopping. All of our robots utilize this basic noggin. On board this noggin is a suite of instruments. We have a magnetometer, a heat sensor, seismometer, retroreflectors, and thermometer. Some of these instruments are active at all times, while others, such as the seismometer, are only active while the robot is not moving. Cameras are situated behind this UV-sensitive window, allowing for 3D projection on Earth. Photovoltaic material on the rear of the robot provides charge to the batteries stored below. These batteries can also recharge from charging stations, which I'll discuss later. Perhaps our most difficult opponent is the lunar dust. We propose that sending a pulse through etching on the surface of the robots will allow propulsion of the dust. As you explore, all the data which you've gathered, including the visual, is synthesized and put into a data-rich map, which can be accessed later. These streams are attached to robot trajectories and replayable as data trails. Here you see the hopper and its associated data trail being generated behind it. Each player contributes a small portion to this data trail. Next, we have the walker, about the size of a toddler. In addition to the standard instruments on the hopper, the walker comes equipped with various spectrometers for rock analysis. With its grasping mechanism and high-res camera, it is capable of getting an even closer look at the surface of the moon. We imagine this robot will be playable with the motion of your body, similar to Xbox Kinect. Explorers would roughly act out what they want the robot to do. Of course, the 2.5-second lag time causes for some karate-like motions. Onboard gyroscopes on the walker allow the robot to have a low-level autonomous balancing. Last in our lineup is the luxury roller with an elevated panoramic camera. This camera allows for a 360-degree projection in your living room for full immersion into your exploration experience. Also special to the roller is its rock analyzer and its capability to serve as a charging station for the walker. Here's the roller in action, examining a crater and beckoning you to come take a look. Placing a sample in the rock analyzer creates a 3D mesh of the rock, which is then saved and location referenced. This can be added to the map, creating a layer of texture. Any rocks which you gather can later be 3D printed as a keepsake of your time on the moon. Our robots will be deployed in groups to multiple sites in multiple phases. Here's a visualization of how the robot's data trails may expand on the moon to eventually cover the entire lunar surface. Scientists can then go to this map, which will be free and open to the public, download the data, and use it in their research. We believe the market already exists for this service, namely those who pay to play for exploration and adventure in virtual worlds. For instance, there are currently 12 million active users to World of Warcraft who pay $15 monthly, generating the company an average of $5 million each day. Additionally, there are millions of people who buy game consoles for use in their home, each game console costing about $200. If we can make our game experience appeal to even a small portion of this population, we can greatly offset the cost of the mission, if not fully cover it. Here's an outline of our 3 main phases. In the alpha phase, we launch to the poles of the moon. This phase is for testing to see what makes the robots break. The beta phase, which launches to the equator, is a test to see how long can we make the robots last. And finally, the last launch, deploying bulk robots to various latitudes on the moon, is the publicly available and most affordable phase. In the alpha and beta phase, we envision that people on Earth would be bidding to be the first to use these robots on the moon and to possibly break them. Here's a simplified version of our calculations. First, we determined what people would be willing to pay for each type of exploration experience. We then estimated manufacturing and shipping costs for each of the robots, and we compared this to the revenue generated by the robots over their lifetime. As you can see, we generated a profit, and we actually found it very easy to break even with enough money to cover R&D and communications cost. In general, we think this would be extremely popular. The moon is visible to everyone on Earth, yet currently unreachable. Who wouldn't want to explore it? By moving away from autonomous robots and centralized mission control, we have the chance to reinvigorate the world's interest in unexplored horizons. This idea is not just applicable to the moon, it's for connecting people to exploration anywhere. I leave you with this slide showing futures of satellite play. Thank you.
We'll have a few minutes for questions from the judging panel.
So, first question: where did you get your cost to the lunar surface, and where would you get your ride?
What was the second part of the question?
Where would you get? Who would provide it?
Okay, we were looking mostly at cost to send per pound, and so there were estimates for cost per pound to send today, which were like $12,000, and we used estimates up to $80,000 per pound, and that's where we got the shipping costs. We didn't really pick a specific person to fly it there. We just looked at the most optimistic and pessimistic values for what it would cost to get there.
So I'm curious how the robots would navigate. How would you know where they are on the moon?
There will probably be a satellite orbiting the moon as well, which the robots will relay information to and then back to the Earth.
You mentioned a little bit about the time delay as you were walking around. Have you thought anything more about that, trying to, controlling over that distance and that lag? Anything you would set up to help it be a little more smooth?
Yeah, so we'll have some autonomous, for example, balancing. We don't want the user to be worried constantly that the robot will fall while there's a time lag. So some of these will be very low-level functions in the robots just to basically maintain themselves and while they're waiting for something, while they're waiting for input.
And if the robot becomes disabled or falls over, is there a plan to recover it, or?
So if the robot is still able to charge, it's still a viable data point, for example, for seismic data. But if not, it's kind of like a carbon oasis on the moon. But with the revenue, there could be potential for collecting dead robots.
So one of the interesting things about this is that you have a really clear sort of business picture of why people would use this and where it would take you. So I'm curious what you think might follow after this. So what's your evil plan for taking over the moon?
Well, the great thing about this is really it's not just for the moon. Like we could explore the world's deserts, very cold places on Earth, the oceans, and all the while people, I think, will be very engaged in getting to be somewhere remotely that, be the first person to see these places.
Discuss the dust issue again. It seems like it might be a problem for your visuals.
Right, so currently lunar dust is a problem for many missions. It gets on the surface, it's hard to get rid of. What we propose is there would be a sort of etching on the surface of the robots, which by sending a pulse through it might be able to propel it, but that will need further testing.
Thank you. The next presentation is by a team of graduate students from the Aero Astro Department, Justin Kaderka, Michal Krachik, and Paulo Mello. Their presentation is called Chain Exploration of the Deep Ocean.
Good afternoon. Thank you, Peter. As you mentioned, we'll be presenting Chain Exploration of the Deep Ocean. I am Justin Kaderka. This is Michal Krachik and Paulo Mello. In 1960, the bathyscaphe Trieste touched down in the deepest part of the ocean. This was in the Challenger Deep in the Mariana Trench and over 10,000 meters deep. When the two men on board looked out through the portal, they saw something that scientists thought was impossible at these crushing depths. They saw life. But since then, scientists have had only fleeting glimpses of what lies in the deep ocean. And this is partly because these organisms do not exist very well in a laboratory setting, but also much of the deep oceans has yet to be explored. Moreover, many new species are being discovered at a yearly rate, as evidenced by recent expeditions. And so there's still many new species yet to be discovered in the deep oceans. Much of the exploration in the past has taken part with remotely operated vehicles, as well as autonomous underwater vehicles. However, while these have taken the pioneering steps to exploring the deep oceans, there is still so much that is left to be explored. Our idea is to explore the deep oceans through the use of autonomous underwater vehicles, but these robots will be able to track and characterize marine life. And by characterize here, I mean track them, but also characterize them in terms of eating habits, as well as mating rituals and so forth. These robots will be able to classify new species, as well as stream data back up to the surface. These robots will be fish-like in nature, in that they will have a tail for propulsion, as well as stabilizing fins. They will have a communication antenna. And in the front, they will have an equipment bay that consists of lights and other sensors, such as HD cameras, IR cameras, and sonar sensor. Now, the idea of how we're going to implement these robots is the crux of our exploration idea, and it's something we're terming chain exploration. Now, imagine you have a swarm of these robots. Now imagine you have a swarm of these robots following a known species, such as a sperm whale. And the sperm whale is known to travel thousands of miles and dive to great depths to catch its food, which partly consists of colossal squid and giant squid. Now, when the sperm whale dives to catch or encounter the squid, the robots that are trailing it will recognize a new organism, and some will branch off and follow the squid, while some remain with the whale for its next encounter. And so forth, the squid will swim along and encounter another organism, which perhaps is new to science at the time, and some robots will branch off and follow the new organisms, while some remain with the squid for, again, its next encounter. And this sort of chain exploration will continue on and on throughout the world's oceans. Now, because of the inherent nature of the chain exploration, these robots will need to be very durable in nature, in that they will need to have very long operating lifespans on the order of years. They will also need to be able to travel thousands of miles, as well as dive to the very depths, the bottom of the ocean. There are many technological challenges associated with this exploration, but however, all of these challenges have basis in the technology of today. Power is one issue, for instance. However, and while a green power that's derived from, say, thermoclines or currents would be ideal, other options are available in the form of a small nuclear reactor or a generator based on radioisotope decay. Communications is another issue, however, there have been several advances in underwater acoustic communications. And we're also exploring the idea of using shadow robots in this exploration idea. And this idea of shadow robots is explained kind of on the image to the right. And if you can imagine, the exploration drone would be on the bottom of the ocean tracking a species, a fish of some sort, and would be relaying information back up to the surface. And if you can imagine, there might need to be an intermediary layer or layers of robots to serve as relay stations or boost the signal. And then at the surface, there'll be a shadow robot tracking the drone underneath it and relay this or convert this information from acoustic signal into an RF signal. And finally, several advances in tracking algorithms will need to be come up with in terms of visual tracking or IR tracking or tracking with acoustic imaging. Now, because data will be streaming to the surface, there is several opportunities for public outreach in terms of pocket aquarium. And this is public outreach in the sense that students or the public can have an app on their smartphone or go to a website and be able to see all the feeds of the different robots. And in this manner, the public will be able to see, for the first time, deep sea organisms in their natural habitats. And this pocket aquarium can also be used in actual aquariums in the sense to augment and expand the current deep sea exhibits. Finally, if this technology is possible in the next 50 years, what's possible in the following 50 years? Can we use this technology, these robots, to explore other celestial bodies that perhaps have deep oceans, such as Enceladus or Europa? And in this manner, provide the path, the initial steps for further human exploration. So with that, thank you very much. I'll take questions.
It looks a lot like bait, but I won't go there. Propulsion, lifespan, you mentioned nuclear. See any issues with your preferred method?
I mean, given the current nuclear crises that are happening in the world, of course sunuclear raises red flags and would be a tough thing to get through politically. However, other forms, such as radioisotope decay, might provide a more reliable option and more politically acceptable, maybe.
So if we were a group of investors and we were asking you how you were going to spend our money on technology development, what do you think are sort of the key technical problems here you'd have to overcome to make this work?
Well, I think one of the key technical issues is tracking. Not only would they have to be able to track these organisms and be able to characterize them and be able to recognize which organism is which, they'll need to be able to do that in the deep ocean where there's little light, and it's so you need to be able to rely on other sensors other than visual in order to be able to track these organisms. I think that's probably going to be a big technological issue.
So just to follow up on that, how do you plan to do the navigation? So how will you know where the vehicles are? And then I got a couple others.
So one can imagine if to know where the vehicles are, they can be relaying GPS, or you can be relaying GPS coordinates down from the shadow robot. So the shadow robot will be directly above the exploration robot at the bottom, and so they'll be able to receive GPS coordinates.
In a couple of your slides, you mentioned that you're going to have IR sensors on the vehicles. Why are you doing that, and do you see any problems with that?
One of the issues with underwater is the murkiness or the depth, and we're not experts in the underwater sensing, and IR is perhaps one way of sensing, but I don't know the full details, and of course you might get some refraction
Our idea was a little bit based, like using this technology was based on the latest development in the night vision, using the IR to have the color image. It's a new developing technology, so that was the reason why.
What about decision? You talked decision making. What the little fish would follow? Who's going to decide? Is there a person in the loop or an algorithm, or how would it know who to break off? Or
I think the idea, because we are envisioning it as a very long process, so it will be basically an algorithm, and the human can interact with it, but the robot has to be able to make his own decision. And that's why also for example, the exact tracking of the robot is not that much doesn't have so much importance, because they will communicate within a group of robots. So,
okay, thanks.
The next presentation is by Mary Knapp, a senior, class of 2011 in the Aero Astro department. Her presentation is called Solara, Exploring the Last Frontier of the Electromagnetic Spectrum.
Thank you very much. Good afternoon, everyone. I'm presenting Solara, and Solara is not so much about exploring a physical place as an unexplored region of the electromagnetic spectrum. Since the very beginning, astronomy has been primarily an observational discipline. And from the beginning, the only detector available to astronomers was the human eye, which is necessarily limited in the wavelengths it can observe. Here we have an image of our galaxy, the Milky Way, in visible light. And this is what the Milky Way would look like if you were able to see the entire sky all at once with high sensitivity. And as you can see, the center of our galaxy is shrouded in dust. And in visible light, we simply can't see through the dust to the heart of our galaxy. But the development of detectors that can see into the infrared range has allowed astronomers to peel back the dust and see into the heart of our galaxy. Here we have 3 images of the Milky Way in near-infrared, mid-infrared, and longer infrared wavelengths. Radio astronomy has offered yet new vistas on our galaxy. And as radio dishes get bigger and interferometry comes into its own, we can probe even deeper into the long wavelength range of the spectrum. But development is not limited to this low-energy, long wavelength area of the EM spectrum. New detectors allow us to see the sky in X-rays, and even in very high-energy gamma rays. So now, astronomers are privileged to have this beautiful multispectral view of our universe, of our galaxy. And as you can see, each distinct region of the spectrum gives a strikingly different portrait of the very same galaxy. So despite these advances, there's still a piece missing. Way up at the various lowest energies of the electromagnetic spectrum, there's a region from 30 megahertz to 30 kilohertz that we have not explored. This is a full 3 orders of magnitude of the electromagnetic spectrum that we simply haven't looked at. The primary reason for this is that these long wavelengths cannot penetrate the Earth's ionosphere and reach the radio telescopes on the ground. So in order to observe this area, we need to put a radio instrument in space. To further complicate matters, these very long wavelengths tend to require very large collecting areas, very large dishes, in order to achieve reasonable spatial resolution, be able to tell one object from another in the sky. So rather than launch a giant radio dish to space, which would be prohibitively expensive, we take advantage of interferometry, which allows us to make a virtual dish of very large proportions out of many small satellites flying in formation. So in order to finally explore this last frontier of our electromagnetic spectrum, we need a space-based interferometric array. So what would this array observe? What will we see when we look? Close to home, we can look at our own sun and observe solar weather, events like coronal mass ejections and solar flares, that not only will give us insight into the inner workings of our own star, but we'll also be able to track these events as they move away from the sun towards the Earth in 3 dimensions and in real time. And once these solar storms reach the Earth, they can have disastrous consequences not only for electronics and vehicles in space, including the space station, but also electronics on the ground. In the past, there have been entire power grids knocked out by powerful solar storms, leaving millions of people without power. Moving farther out in the galaxy, Solara will be able to look at exoplanets in the radio. We know from observing in our own solar system that planets with strong magnetic fields emit strongly in this long wavelength radio band. So observing exoplanets in long wavelength radio will give us insight into their magnetic field structure and therefore their internal structure in a way that current technology simply does not give us. We may also be able to detect new planets this way. And moving even farther out, there's never been a full sky map in these frequencies. So Solara will be the first to look at our universe in very long wavelengths. We know that from history that map making is a critical first step towards exploring new territory. So we hope with Solara, when we map the sky in these long wavelengths, we may discover brand new phenomena that are not visible in other wavelengths. When astronomers first observed the sky in microwaves, we found the cosmic microwave background, which has fundamentally changed the field of cosmology and our understanding of how the universe came to be. So Solara has the potential to unlock similar secrets about how the universe works. So given these important science goals, what sort of instrument do we need to make these observations? I'm proposing a CubeSat constellation implementation. So CubeSats are small satellites, approximately this size, that are launched as secondary payloads on other rockets, so you don't have to pay for your own rocket. So imagine a spacecraft this size with antennas that span the entire size of this auditorium. And now imagine 12 of these in a constellation with the nearest one to this particular spacecraft perhaps as far away as Lexington, and the farthest as far away as Springfield. So 12 of these would form a constellation of approximately 10 to 100 kilometers. And CubeSats are especially good for current space exploration because they're low cost. They use off-the-shelf components, and as I mentioned, they piggyback on other launch vehicles. So the instrumentation needed for Solara is also fairly simple and cheap. It's simply radio antennas and radio receivers. This technology has been used on the ground for decades. It's cheap, it's well understood, and it's very hardy to the space environment. We would not need clean, fragile optics or cryogenically cooled detectors. And finally, the interferometric techniques necessary to make these images in long wavelength radio have been used on the ground for decades as well. And so we'll simply transplant that knowledge from ground-based systems to space. So to conclude, this Solara offers us the opportunity to explore uncharted territory using well-understood techniques and technology. We'll use off-the-shelf components whenever possible to reduce cost, and the constellation concept will reduce risk because it's very redundant. If a single element fails, we can still take data with the other 11 remaining spacecraft. This will also serve as an engineering testbed for formation flight, which will allow future missions to use this technique with higher confidence. And finally, Solara will spur development in small satellite technology, specifically the areas of propulsion, fractionated spacecraft, and deployables like those very long antennas that I mentioned a moment ago. So we hope that Solara will not only bring in important science returns in its own right, but also generate a toolkit for future explorers to use in answering questions about the universe and our place within it. Thank you very much.
You mentioned this is an advantage over ground-based observatories. I mean, we have space observatories, Hubble and Chandra, and up there. They don't cover this spectrum, and I'm just wondering why have we missed this over all the years with even with the space-based observatories that we have?
That's a very good question, and the answer, I think, is that in order to really effectively observe at these very long wavelengths, you really need an interferometer. You need multiple elements spread out over a wide area, because a single dish, you just can't build a big enough one at a reasonable cost. And so that's been the holdup, is formation flying hasn't quite gotten to the point that it needs to be for us to confidently launch a mission that is an interferometer.
You sort of argued that you're going to have this distributed CubeSat approach. Do you see that do you envision that you would have to control the position, or are you just going to let the vehicles drift and use whatever position you would get, and then how would you know where they are?
That's an excellent question and a critical technical challenge. The nice thing about these long wavelengths is you don't need to control the position of each spacecraft very precisely, but you do need to measure it precisely, and measurement is a lot easier than control in this case. So the spacecraft will be allowed to drift until one of them is too far outside the constellation and needs a kick to be brought back in line with the others. So there's very little control necessary, but measurement is a challenge.
So can you talk about what happens with the data that you generate from these CubeSats? It comes back down to ground, and what kind of processing is required to make sense of this?
Another excellent question. There's actually a significant amount of processing that needs to happen to transform the signals from all of these spacecraft into an image. But luckily, that can be done on the ground. So the raw data will simply be transmitted from each spacecraft, possibly through sort of a mothership communication spacecraft, to the ground. And then on the ground, it goes through a number of steps. The most computationally intensive, I suppose, is a three-dimensional Fourier transform.
I like the fact you're using lower risk technology in some of the systems, and I like the CubeSat approach. You said that ride shares are free, and there's real cost associated with rideshare. But if you were to estimate the total cost of your project over the next 5 or 10 years, however long it's going to take, what is that timeline, and how much do you expect it'll cost to launch this constellation?
So I would expect that to develop the first unit, the prototype, it would cost on the order of a few million. And then after that, all the others are copies. So you're paying essentially for the labor to assemble them and the components. So the copies might be on the order of 300,000 to 500,000. And so you could put together a fleet of these for a reasonably low cost compared to, say, the lowest cost NASA missions. As far as launch, there would be cost. You're absolutely correct that there would be costs associated with that. But since you would still be a secondary payload, it's not going to be the same as purchasing your own launch vehicle, which would be hundreds of millions. It's very, very expensive.
Don't rule out nanosat launchers off of suborbital vehicles.
Absolutely. Absolutely.
Paid advertisement.
That would be wonderful.
The next presentation is by a freshman, James Penna. James recently declared a major in physics, and he'll be talking about Jupiter, our gateway to the stars.
Ladies and gentlemen, I present to you the future of our interstellar exploration program, Jupiter. Now then, you may ask, how can what planetary scientists consider the failed attempt at a star provide the gateway to our own future? I will show you. Come on now. There we go. Now then, we are about to embark on the most massive construction project in human history. We're going to need a good reason to do this. Ladies and gentlemen, we are entering an era in which dozens of planets discovered every year are blossoming into hundreds. Eventually, we will find one that looks kind of similar to home and is kind of nearby. I think that it would be imperative that we send someone, or at least some robot there, to investigate whether or not there's life. Also, Earth is fragile. We float like a mote of dust in God's eye. Something may happen to us. It'd be nice to send people to a place that looks kind of like home, preserve our species. It may be argued that it is our destiny to expand to the stars, to allow our species to proliferate. And of course, there's the most interesting possibility. There may be someone out there who starts calling us, and they want us to drop on by. Now then, the plan I propose is first for the establishment of a permanent manned base on one of the Jovian moons. So that way we may begin the utilization and development of the Jovian resources for our ultimate goal, the construction of multiple fast subluminal spacecraft to local star systems. Now let us first look at the resources Jupiter itself has to offer. We see here helium-3 in vast quantities, higher than any other body in the solar system, nearly 1 in 100,000 parts, as compared to 1 in 4 million parts in lunar regolith, which has gotten so much attention in the press lately. We will use that for fusion fuel for our spacecraft, which I will mention later. Jupiter's proximity to the asteroid belt also gives us easy access to construction materials and metals for refinement. Jupiter's moons also makes it a particularly attractive prospect for our colonization. We see that 3 of the Jovian moons, Ganymede, Callisto, and Europa, are known to have water or water ice in some form. We can use that for human sustainability, oxygen, growing plants, of course, to feed our people, chemical fuels, fuel cells, and most importantly for this project, the harvesting of deuterium as fusion fuel for our manned interstellar spacecraft. Now then, the particular setup I propose is first the establishment of a manned base on Callisto. Callisto is the farthest out of the Galilean moons and receives, as such, a minimum dose of radiation from Jupiter's fearsome gas, as well as being far outside of its gravity well to allow the fast launch of vehicles without any expenditure of major energy. It also has water, which is important, as I mentioned, for human sustainability and deuterium harvesting. We will then dot the skies of Jupiter with automated gas drones, which will harvest the helium-3 for us and return it via coil gun. Now, this is a system of solenoids driven by the electromagnetic force, requiring no fuel, no propellants, just simple electricity to drive out the gas that we need from Jupiter to the asteroid belt. The main asteroid belt will be mined by both manned and unmanned systems, which will extract the metals we need to begin construction on our spacecraft. Now then, by no stretch of the imagination is space expensive. We will need lots and lots of cash to do this. So I propose that first we outreach to energy companies and offer them stakes in helium-3 mining operations on Jupiter. This will allow them to retain some of the helium-3 for themselves, producing clean energy here on Earth at a profit to this project. We will then outreach to private investors. Some of you out here may have a stock portfolio. Perhaps you'd like to diversify by investing in asteroid metal refining operations. By the by, the current market value of platinum, rare on Earth but common in the asteroids, or at least relatively, is $1,800 a troy ounce. Now then, this will allow us to decouple funding from the government into the hands of private investors, at least allowing us the ability to carry on exploration without the need for pure government funding. Now then, the main purpose of this project is to build interstellar spacecraft, of which I propose both the laser-driven light sail and the Bussard ramjet. The light sail will be driven by fusion-powered lasers on Jupiter's asteroids and moons, which will push it forward at incredible fractions of the speed of light using photonic pressure. This is a proven technology. This is Japan's light sail right here. These will be followed up by manned Bussard ramjets, catalyzed by the fusion fuel from Europa and Jupiter, the deuterium, Callisto and Jupiter, the helium-3 and deuterium. We'll push it forward at first, at which point it will convert to ramjet mode, taking in interstellar hydrogen and compressing it, allowing our astronauts to accelerate further to their destinations in reasonable amounts of time. Now then, I foresee us sending fast interstellar light sails to prospective planetary systems, scoping out the territory for us, telling us about these planets. We will then follow up these light sail expeditions with manned Bassar-driven ramjets with our colonists, and we will eventually colonize the galaxy at large at one point by this method, or at least I hope so. Now then, this will have major impacts on the scientific community. First of all, this would be worth the trip alone, I think. By having a manned base in the Jovian system, we would gather terabytes of data on Jupiter, allowing us to analyze it and refine theories of planetary formation, of gas giant structure and composition. But, of course, we are here for traveling to other stars as well. So that kind of speaks for itself. We will have the ability to study other stars, other planetary systems in depth, discover life, colonize the galaxy. It will be a new era in human information, the true exploration of the cosmos beyond our solar system. Now then, I'd just like to end up with some perspective here. Dr. Carl Sagan, one of the inspirations for this project, once said, "A still more glorious dawn awaits us, not a sunrise, but a galaxy rise, a morning filled with 400 billion suns." To try and answer Dr. Sagan, it's time we start filling up that morning sky.
So how big do you envision your colonies to be? How many people in the colony?
Well, at first, we'd probably be sending about 6 or 7 people just to establish a foothold, build up, infrastructure, probably radiation shielding out of the ice, construct habitat modules, automated systems to the asteroid belt at first. But then I foresee not regular, but at least semi-regular launches sending 10 or 20 more. We only need people really on Callisto. I believe that automated systems in the asteroid belt would suffice, especially considering they can be self-replicating, allowing them to build up over time.
Who would be building these self-replicating? There'll be robots that are going to build the robots for you?
Well, robots can build robots. If we send over perhaps 1 or 2 robots at first, we have them build up their own brethren and then commence mining operations.
For the harvesting of the helium-3 and the resources, do you really need the people for that? And, I know you talked about trying to get energy companies interested in that, but can you do that autonomously? Why do we need the...
Oh, no, we wouldn't be sending people into Jupiter's atmosphere. That'd be much too dangerous. They will be automated drones. Energy companies would help fund these drones and give us, capital for drones in Jupiter. But no, I would never send anyone to Jupiter's atmosphere. The radiation is far too dangerous. So they'd be automated mines.
Talk to me more about platinum and how are you going to get it back?
All right, well, I envision a system similar to the coil gun return system for helium-3 shipments. Now, the reason why I choose platinum, iridium, and rhodium in particular is because they offer the highest value-to-weight ratio. I mean, it's never cheap to send anything into or from space. So you want to ship back what's valuable and as much of that as you can, as opposed to common ores like iron or aluminum, which we can get here on Earth. So we want the most valuable stuff, the most bang for our buck, if you will.
So this is certainly a vision with a capital V. Can you help us sort of understand, what the stepping stones are between here and your final vision of sending things to the star? I mean, if you're going to describe what are the set of technologies you start with first, what does that get you, and then how do you take this sort of one piece at a time?
Well, just one piece at a time. First, I'd recommend sending robots to begin mining operations in the asteroid belt. That will probably run up somewhere around $500 million if you look at recent missions to asteroids like Levy Shoemaker or the Japanese Hayabusa mission. I would then recommend we send people to Callisto, the initial colonizers, to help form the habitats. NASA's HOPE study, Human Outer Planetary Exploration study, said that perhaps we could launch people to Callisto as early as 2045. Then again, that was 2003 NASA.
Our final presentation will be made by a team of Aero Astrograd students Rachel Foreman and Aaron Johnson. Their presentation is titled Lifelike Robotic Birds for Remote Exploration of the Amazon Rainforest.
Good afternoon, and welcome to the MIT Museum. I'm Aaron Johnson, Education Coordinator.
And I'm Dr. Rachel Foreman, Director of Technology. Thank you for joining us for this special part of MIT's bicentennial celebration. Most of the explorations you hear about today are deep within the ocean, or on the moon, Mars, or beyond. So it's natural to assume that since we're traipsing about the heavens, we understand everything about the surface of our planet. That's simply not the case. Amazingly, there's a region of Earth bigger than the continental United States, yet largely unexplored. And this isn't a barren desert or a cold, lifeless ice cap. Rather, it's home to 1 in 10 of Earth's known living species. That includes some 2.5 million insect species, 400,000 plants, and about 2,000 birds and mammals. What is this great mysterious place? The Amazon rainforest of South America. Until recently, it was virtually impossible for humans to explore the Amazon due to its density and enormous size. About 16 months ago, this all changed with the introduction of an explorer that nature has already optimized for the environment. These are robotic birds that contain advanced sensors and 3D high-definition video cameras, yet mimic the look and flight of real birds. Through the combination of many advanced technologies, they've been able to remotely bring scientists, students, and the general public into the rainforest. So how do these explorers work? In terms of flight, essentially the same as living birds. Synthetic muscles allow the bird's wings to flap up and down. Each wing isn't just one rigid piece, like for the first robotic birds 50 years ago. Rigid wings caused a lot of drag and didn't produce much net lift. Our robotic birds have flexible wings, and they can twist or morph to provide both lift and thrust. This motion is very efficient, as the wings and feathers can position themselves perfectly for minimum drag and maximum power. The aerodynamics are complex, connected to the structural dynamics of the wings and the stability of the entire bird. While we started to unravel this puzzle 50 years ago, it's only now that we can put it to such spectacular use. After the birds are deployed in the Amazon, they operate either autonomously or with augmented human control. In either mode, tiny, high-definition 3D video cameras continuously gather data about the environment. Advanced processors, essentially the bird's brain, use this information to quickly generate a 3D path. So when scientists are piloting a bird, they don't have to worry about avoiding every single tree branch. They just specify a general direction, and the autonomous systems plan the way. This autonomous path planning ability was one of the major driving factors required for the bird's success. In the past, the vast majority of robotic birds were entirely remote controlled. Some mobile systems, like ground robots and flying quadrotors, could operate autonomously, but the dynamics of robotic birds were just too complex. Only recently have 3D path planning algorithms become adept enough to allow robotic birds to fly with the speed and agility of actual birds. These algorithms have to deal with a huge amount of information during flight. They have to plan a three-dimensional path around many rapidly changing obstacles, and there's a lot of uncertainty in the environment. These are challenges that path planning algorithms couldn't even begin to handle 50 years ago. To talk about how these robotic birds have been quite the boon to scientists, biologist Robert Green is joining us live from the Edward Stafford Field Station in the Peruvian Amazon. Dr. Green is an MIT alumnus who's now a researcher with the University of Michigan. Thanks for joining us, Dr. Green.
Thank you, Dr. Foreman. I've been working with a flock of these robotic birds for about a year now. We've already made incredible advances in our research thanks to them. One of the great things about these explorers is how they actually look like indigenous birds, scarlet macaws in our case. This camouflage prevents them from appearing intrusive and then just frightening the wildlife. I mean, you can imagine that if we used quadrotors or other micro-air vehicles, we'd have a heck of a time getting close to any of the animals. One of the great things about the birds is how they can use their HD cameras or other sensors to automatically identify and then catalog the plant and animal species that they see. So we just send them into the rainforest and we get back a list of organisms and where they're located. Most importantly, though, the birds can notify us when they think they've found an undiscovered species. We don't have to personally examine each video frame, which is something that my graduate students certainly enjoy. And then when we find areas of high biodiversity or scientific value, then we can head into the rainforest and collect data ourselves. So using these methods, our team alone has discovered 120 organisms in the past year. That's about one every third day. We're certainly not slowing down.
Input, Dr. Green.
You're very welcome. These robotic birds have proven to be an incredible benefit to scientists, but they're not the only ones who can participate in the birds' explorations. High-definition 3D video is streamed live over the internet. With your standard home telepresence system's wraparound visor, you can become totally immersed in a real-time, first-person view of the rainforest. We also provide live audio captured by the birds' high-definition microphones. So, with this immersive technology, you really feel like you are a bird, swooping and soaring through the Amazon. That video is just a glimpse of the experience we can deliver. You really do have to try it out for yourselves. What's most exciting is that every day the birds provide the first view into completely new locations, finding plants and animals never before seen by human eyes. They really are increasing our knowledge of our own planet daily, and you personally can have a front row seat. In honor of MIT's bicentennial, we are very pleased to announce that we've partnered with Dr. Green's team, allowing visitors the ability to fly the robotic birds from right here in Cambridge. Everyone, especially students, will have the opportunity to really become an Amazon explorer themselves, piloting the birds into uncharted territory. So we hope that you'll come back and fly the birds soon. Remember, as Dr. Green said, his team is finding a previously undiscovered species once every 3 days. Will you be at the controls the next time they do? I'll be happy to take questions in either of my characters now.
So this is compelling, but what do you think the range of your vehicle, what's the range of your lifelike birds, and what's your power source?
Yeah, so in terms of range, we really expect it to be able to travel all over the Amazon. It's such a large area, and we hope that sort of with a large team or a distributed team of birds across really the whole rainforest that we can cover a large portion of it. In terms of power source, looking at a number of opportunities, perhaps sort of as was talked about earlier, we can do more with slight increases in battery power just because we have more capabilities. Also perhaps solar power integrated into the bird where maybe if they need a charge, they can go up above the canopy. And if the efficiency of solar panels keeps increasing, they'll need to spend less and less time recharging.
I think you mentioned something here about collision avoidance tracking. What about things you might not be able to control, like another bird, a lightning strike? I mean, something eventually may happen to one of these things. How would you deal with that?
Yeah, that's true. So we hope that sort of with the autonomy that we have, we can avoid predators and risk as much as possible, but the risk is certainly inherent to the mission. And so hopefully in the future, we'll be able to produce a lot of these birds cheaply, and so that if something happens, if one does get struck by lightning or attacked by a predator, it's not a huge loss. We have them all over the continent, and we can go out and get another one and send it out in its place.
One of the important things about an exploration company is the ability to identify the long-term vision, but also figuring out how to get there along the way without sufficient amounts of capital. We'll call it the bootstrapping method. Sometimes you find customers along the way. Clearly this technology has other applications. Where do you see this developing in the next, we're now 2011, you've got a view of 2060. What other uses do you see this technology generating?
There's definitely a lot of uses along the way. I think sort of the first step is getting the birds that can fly like actual birds, perhaps minus the complex autonomy part, because that's a benefit to the military. The military is, for example, looking at small birds that soldiers can carry for recon and things like that. So that could be something that could be done without the autonomy. I think that's the first step. And when you add the autonomy, it just, you can use it for remote exploration like this or other tasks. That autonomy itself is also not just for robotic birds. If you develop that autonomy, you can use it in tons of different systems, really all over. So that, I guess that piece has applicability here, but elsewhere as well.
So I'll ask you kind of a tricky question, which is, tell me which of the technologies in here you're least certain of, and what would be your mitigation strategy? How would you realize your vision if it failed?
Okay, what is the trickiest technology? I think one of the tricky technologies is sort of the machine vision component of it, where you have to, because we rely on these sort of 3D high definition cameras to be able to see the rainforest, resolve this is a known species, this is an unknown species, this is a branch right in front of me. I think sort of relying on vision, there are other sensors that we could use. We could use sonar or other sensors to sort of identify obstacles. If we needed to help put a human in the loop, perhaps to resolve organisms or identify organisms, that would be a possibility. Ideally, we'd like to have that machine vision, but I think there are other ways to still get the same end result if that wouldn't come about. All right, thanks.
And thank you again to XCOR Aerospace. That was our last presentation, but the competition is not quite finished yet. In a moment, right now, we have information on text message voting on the screen. SMS voting will only be open for about 10 minutes, so we encourage you to take a minute to vote for one of these teams. Make sure that the text votes are spelled as you see on the screen, and all lowercase letters. The audience voting will be entered into a formula along with the judges' rankings, and the winners will be announced tomorrow morning here at 8:45 a.m., so we hope to see you then. Thank you.